Functional Semiconductors continuing series of online webcasts. My name is Bob Bell. I'm an application engineer from Phoenix, Arizona. Today's topic is an introduction to a family of integrated buck regulators using a new form of control that we refer to as emulated current mode control. The topics I plan to cover in this presentation are buck regulator basics, operation of current mode control, operation of emulated current mode control, a new family of simple switcher regulators, thermal considerations, loop compensation design, and an introduction to an inverting buck boost application. Shown on this slide is the power stage for a step-down buck regulator. The output voltage is stepped down by modulating the duty cycle of the MOSFET Q1. When the MOSFET turns on, Vin is applied to the LC output filter. The transfer function of this regulator is Vout equals D times Vin, where D is the duty cycle of the modulating switch Q1. The diode D1 provides a path for the inductor current to flow when Q1 is turned off. Each cycle, the inductor current ramps up while Q1 is turned on and then ramps down while the diode is conducting. The MOSFET and diode currents sum to form the inductor current. The current waveforms are shown on the slide. Shown on this slide is the same basic buck regulator power stage with the addition of the control circuitry. Control is accomplished through pulse width modulation of Q1. This particular control circuit is referred to as current mode control. The main characteristics of current mode control is that the modulating ramp used by the PWM comparator is a signal derived from the buck switch current. When the buck switch is turned on, the current rises with the same profile as the inductor current. Each period, the modulation of Q1 is controlled as follows. First, the clock period expires and it sets the RS flip-flop, setting the output high. Then the level shifter and switch gate driver activates to turn on Q1. When Q1 turns on, it immediately transfers the current which was flowing in the diode D1, and that's why there's an immediate step or a pedestal in the current profile of Q1. As Q1 continues to stay on, the current continues to ramp. There's a current measuring circuit which measures the current through Q1, and as that current continues to ramp, it applies a signal to the PWM comparator that's proportional to the current through the inductor and the current through Q1. When that signal reaches the same level as the error amplifier signal, it trips the PWM comparator, which resets the RS flip-flop, which then turns off, or starts the driver to turn off, which then turns off Q1. It can be seen that there are quite a few steps that need to be accomplished each period. The minimum time required to complete these steps creates a minimum controllable on-time or duty cycle. For large step-down applications with a large input voltage and a much smaller output voltage, this minimum on-time can present a problem. The biggest challenge when designing for minimum on-time is the design of the current measurement circuit. We'll talk more about this in the following slides. The objective of this presentation is not to cover every detail of current mode control, but I would like to list the common main advantages and disadvantages associated with current mode control. Current mode control acts as a single pole system. The measurement of the current forces the inductor to act as a constant current source. Current mode control remains a single pole system regardless of conduction mode, whether the inductor current is in continuous mode or discontinuous mode. There's also what's referred to as inherent line feed forward. Since the ramp slope is set by the input voltage, changes to the input voltage are immediately represented in the current waveform. By clamping the error signal, peak current limiting can be implemented. And it also has the ability to easily share multiple power converters. The main disadvantage of current mode control is susceptibility to noise in the current signal. This is a very common problem. This reduces the ability to process very small on times, which limits the ability to have large step-down ratios at relatively high frequencies. Another minor disadvantage is that as the duty cycles approach 50% and greater, current mode control exhibits subharmonic oscillation. A fixed slope ramp signal is generally added to correct this. Step-down switching regulators designed for high input voltages must control very short minimum on times to operate at high frequencies. The maximum switching frequency and the size of the inductor and the output capacitor are a function of the frequency, which is forced by the minimum on time. The on time of conventional current mode controllers is limited by the current measurement delays and what's referred to as a leading edge spike of the current sense signal. When the buck FET or MOSFET turns on and the diode turns off, a large reverse recovery current flows. This current can trip the PWM comparator, forcing a premature turn-off of the switch. Generally, additional filtering and or leading edge blanking is necessary to prevent this. An emulated signal is free of this noise and turn-on spikes. Shown on the slide is a typical measurement of a buck switch turning on in a buck application. Shown on this slide is a buck regulator power stage comprised of Q1, D1, L1, and C out. The objective is to create a signal that accurately represents the current through the buck switch Q1 without actually making a direct measurement. When we study the characteristics of the buck switch current signal, we can note that the signal can be broken down into two parts, a pedestal and a ramp. When the buck switch initially turns on, the current level jumps to the same level that was conducting previously through the diode D1. By taking a sample and hold measurement of the diode current just before turning on the buck switch, we can establish this pedestal level. A small current sense resistor is placed in series with the diode anode to accomplish this measurement. Once the buck switch is turned on, the characteristics of the ramping current is the IDT equals V in minus V out divided by L. This is the basic inductor equation. To emulate the ramping portion of the buck switch signal, first we create a current source proportional to the difference between the input and the output voltage. If this current source flows into a capacitor, the ramping voltage across the capacitor will equal dV dt equals V in minus V out divided by C ramp. If we set the value of this ramp capacitor proportional to the input to the inductor value, we can scale the capacitor voltage to match the ramping current signal. The final step is to add the sample and hold of the diode current level to the capacitor ramp voltage. Now we have recreated the buck switch signal with no delays and no leading edge noise spike. We can now use this signal for pulse width modulation and current limit purposes as in conventional current mode control. Each period after the buck switch turns off, the ramp capacitor is discharged in preparation for the next cycle. Shown on this slide is a timing diagram for the buck regulator power stage. You can see how the inductor current is the sum of the buck switch current and the diode currents. The sample and hold is accomplished at the times indicated by the yellow bars. This sample and hold establishes the pedestal level. Shown on the bottom is the emulated ramp signal, which in this case is scaled to 0.5 volts per amp. Applications requiring a high operating frequency along with a large step-down ratio require the controller to have the ability to control the smallest possible minimum on times. For applications with a large V in and a small V out, the minimum on time may limit the maximum frequency. Our new simple switcher regulators can achieve an on time of 80 nanoseconds. The equation for the maximum switching frequency versus V out, V in, and T on min is shown on this slide. Shown on this graph is a plot of maximum operating frequency versus output voltage for two different IC regulators with the input voltage set to 36 volts. Due to the minimum on-time constraints that we discussed on the previous slide, if the input voltage is set relatively high, 36 volts in this case, the operating frequency may be limited depending upon the output voltage. Shown in blue is the maximum operating frequency versus output voltage for the LM2557X family of switching regulators. These devices have a maximum rated operating frequency of 1 megahertz with a minimum on time of 80 nanoseconds. Shown in orange is a competitor device with a maximum rated operating frequency of 2.8 megahertz, yet this device has a minimum on time of 150 nanoseconds. So if the input voltage is set to the maximum of 36 and the output voltage, for example, is set to 3.3, this device can only operate at 700 kilohertz, far less than the claim of 2.8 megahertz. On the past two slides, we looked at how the operating frequency may be limited due to the minimum duty cycle caused by the minimum on time. At the other extreme, if the controller's maximum duty cycle is limited to anything less than 100%, then the maximum operating frequency may also be limited by the minimum input voltage. On the past two slides, we looked at how the maximum operating frequency may be limited due to the minimum duty cycle caused by the minimum on time. At the other extreme, if the controller's maximum duty cycle is limited to anything less than 100%, then the maximum operating frequency may be limited and the minimum input voltage may be limited. For the emulated current mode control concept, there is a forced off time each cycle of 500 nanoseconds. This forced off time is necessary to allow time for the sample and hold of the diode current. This forced off time creates a maximum duty cycle limit of 1 minus 500 nanoseconds times the frequency. Ideally, for a buck regulator, the output voltage will remain in regulation even when the input voltage is reduced to almost equal to the output voltage. The maximum duty cycle limit requires the input voltage to be higher than the output voltage. The minimum input voltage predicted in the above equation is the lowest input voltage where the output voltage can still remain within regulation. Current mode controlled power converters operating at duty cycles greater than 50% are prone to subharmonic oscillation. Disturbances in peak rising current, delta I, increase at the end of each cycle, causing alternating large and small duty cycles. Fortunately, the solution to subharmonic oscillation issue is easy to solve. The most common solution is to add additional fixed slope to the current sense ramp. Usually the fixed slope ramp is derived from the main oscillator. For the emulated current mode control method, a 25 microamp offset in the ramp current source provides additional fixed slope for this emulation ramp to correct the subharmonic oscillation. An additional benefit of ECM, or emulated current mode, is what's referred to as look-ahead current limiting. Since the inductor current is measured near the end of the diode conduction time prior to turning on the buck switch, during high input voltage, extreme short circuit conditions, the buck switch will actually skip cycles if the inductor current does not decay below the current limit threshold during the off time. Skipping cycles prevents the possibility of a runaway inductor current and provides a very robust overcurrent protection scheme. Each of the newly released regulators has a dedicated oscillator sync pin, allowing the regulator to be synchronized to an external clock, or like regulators, can be connected together to self-synchronize. Synchronizing switching regulators reduces system EMI emissions. For the external sync method, an open drain discharge device is necessary, as shown. To synchronize like regulators, simply connect the sync pins together, and the fastest regulator will act as a master while the balance act as slaves. National Semiconductor is a leader in integrated switching buck regulators with a long history. The latest, newest devices utilizing emulated current mode control allow for a higher input voltage capability and higher operating frequencies than the fixed frequency predecessors. The ability to adjust the operating frequency allows the user to trade off solution size and efficiency. 500 kilohertz is shown as a practical maximum for devices rated to 75 volts, while the lower voltage devices can operate from 100 kilohertz to 1 megahertz. Shown on this slide is a buck regulator application using one of our new integrated switching regulators. The new family of regulators employs the current emulated current mode control technology. There are a total of 8 devices available with either a 42 volt or 75 volt maximum input voltage, and the current maximum levels are 0.5, 1.5, 2.5, and 3 amps. Each device contains a soft start, oscillator sync, remote shutdown capability, and thermal shutdown protection. The higher current devices are available in a TSOP EP package with an exposed pad on the underside to aid thermal dissipation. This matrix is a handy guide for selection of the new ECM devices. Shown are the voltage and current ratings, as well as scale factors and MOSFET characteristics. Shown on this slide is the detailed block diagram of the evaluation board schematic for a 5 volt output buck regulator with a 3 amp current capability. The integrated buck FET has a 75 volt rating. The anode of the external diode connects to ground through the regulator's internal current sense resistor. This application operates at a switching frequency of 300 kilohertz. Shown on this slide is a picture of one of the available evaluation boards. The schematic for this board was presented on the previous slide. Shown on this slide is an efficiency plot versus line and load for a 2.5 amp evaluation board. For current levels greater than 1 amp, the efficiency stays relatively flat, while increasing the input voltage has a negative effect upon the efficiency. Increasing the switching frequency would also have a negative effect upon the efficiency. This particular data was taken at 300 kilohertz. Besides narrow duty cycles, another challenge when designing high input voltage buck regulators is the power loss due to bias power. Bias power is the power necessary to power the controller and drive the MOSFET. As an example, the LM5005 consumes about 8 milliamps while operating at 300 kilohertz. At 75 volt input, this equates to 0.6 watts dissipated in the controller just for bias power. Fortunately, there are several ways to reduce this power dissipation. Shown on this slide are 2 methods of providing bias voltage from the output. This greatly reduces the bias power losses. Shown on this slide is the same efficiency versus line and load graph that we looked at a few slides back. This graph, however, was taken with the controller VCC biased externally. You can see a significant improvement, especially at higher input voltages and light loading conditions. The next few slides will detail several aspects of thermal design. Junction-to-Ambient thermal resistance, theta JA, is application dependent. The actual thermal resistance varies with device packaging type, number and diameter of vias underneath the exposed pad, area and thickness of the ground plane, and the quantity of forced air cooling and total PC board area. The units of thermal resistance are degrees C per watt. If you know the power dissipated in the device, then the junction temperature can be predicted as Tj equals Ta, the ambient temperature, plus the product of the power dissipation times the theta Ja. For the LM5005 demo board, there are 5 vias underneath the regulator IC to connect the underside exposed pad to the ground plane. The ground plane has an area of 1.5 square inches and is made of 2-ounce copper. For the test data that we took in a controlled environment, we did it at various airflows, referred to as cubic linear feet per minute. So for no airflow, the theta Ja measured was 44 degrees C per watt, and that went down to 23 degrees C per watt for 900 LFM of airflow. Shown on this slide is the same 2.5 amp evaluation board that we looked at earlier. This 2-layer PC board has several features to aid the thermal design. The 2 highest dissipating devices are the regulator IC and the diode. Each of these devices have exposed underside pads, and the PC board has several vias to couple the heat to the larger copper areas, aiding in power dissipation. Junction-to-Case thermal resistance, theta Jc, has little application dependence. The units of thermal resistance are the same, degrees C per watt. In this case, though, if you know the power dissipated and you know the case temperature of the device, then the junction temperature can be predicted as the case temperature plus the product of the power dissipated times the theta Jc. For the new simple switcher devices, they're available in 3 different packages, which I'll explain later. But for the LM5005 and the LM5576, the junction-to-case thermal resistance is measured at 6 degrees C per watt. For the LM5575, it's 14 degrees C per watt, and for the LM5574, which does not have an exposed pad underneath, it rises to 30 degrees C per watt. The highest power dissipating components on our buck regulator applications is the regulator IC, the recirculating diode, the inductor, and the snubber resistor, if a snubber is provided. An approximation for the diode power is the output current times the voltage drop of the diode times 1 minus the duty cycle. An approximation for the inductor power dissipation is I squared of the output current times the equivalent internal resistance, DC resistance of the inductor, times a factor of 1.3, which accounts for the temperature and AC losses. If a snubber is used across the diode, an approximation for the snubber power resistor is Vin squared times C times F times 0.75. The IC regulator power dissipation varies with input voltage, output current, and frequency. The easiest and most accurate approach is to subtract the output power and other known component losses from the input power. We'll look more at this at the next slide. The objective now is going to be to predict the regulator junction temperature. First thing that we're going to do is we're going to measure the input power. It's pretty easy to do. We're going to measure the output power. Then we're going to calculate, given the equations that we saw in the previous slide, the diode power dissipation, the inductor power dissipation, and the snubber power dissipation. Then we're going to subtract the input power minus the output power minus the diode minus the inductor minus the snubber. That's going to leave us with the power dissipated in the regulator IC. And then lastly, we can predict the junction temperature by measuring the case temperature times the power dissipated in the device times the theta Jc for the device. Shown on this slide is the first step in determining the regulator junction temperature. This data was taken from the efficiency graphs that we looked at earlier. Instead of calculating P out divided by P in, we are subtracting P in minus P out. The difference in power is the total power dissipated in the conversion process, which has to be dissipated on the board itself. Taking the previous graph and subtracting the power dissipated in the inductor, the diode, and the snubber leaves the power dissipated in the IC regulator. Finally, if we take the previous graph and multiply by the regulator's thermal resistance, theta JC, and add the measured case temperature, that'll leave us with a graph of the junction temperature versus line and load. Generally, a typical user need not go through this entire exercise. One or two worst case points will suffice. I did a more rigorous evaluation here for illustration purposes. One big advantage of current mode control is the robustness and high performance of the loop dynamics. Current mode control can be modeled as a single pole system. Only the output load resistance and capacitance affect the loop characteristics. The inductor acts as a current source and does not play into the loop dynamics. Another advantage of current mode control is the input voltage changes are immediately compensated for, referred to as feed forward. The first step in understanding loop compensation is to develop an understanding of a good working small signal model. The term loop gain refers to the gain of the loop shown in blue. This loop can be broken down into two parts. First, the power stage, the gain from the comp input to the output voltage. The DC part of this is simply the load resistance times the transconductance of the power stage. Also, there is a pole at 1 over 2 pi RL CL. The second part of the loop gain is the error amplifier. The compensation characteristics of the error amplifier have a high DC gain and a 0 to compensate for the power stage pole. The next few slides presents a graphical representation of this model. Shown in this slide is a Bode plot for a current mode regulator. The units of gain are in dB. Remember, addition of terms in dB is the same as multiplication. The loop gain on this plot is the sum of the power stage and error amplifier gains. If we plot the power stage gain characteristics shown as comp to output and also draw a target loop gain, we can see the desired characteristics of the compensation network as the difference between these two. Selecting an overall loop gain with a slope of minus 20 dB per decade ensures a stable loop with 90 degrees of phase margin. From the previous slide, we determined the shape of the error amplifier characteristics. The basic shape requires a high DC gain with a pole at unity and a 0 to cancel the power stage pole. Fortunately, if you did not get all of this, I included several quick equations on this slide to select compensation values. Also, there is an online design tool to help select compensation components and view the model predictions of the loop. I'll present this tool at the end of the presentation. The final loop gain measurements are shown on this graph. The crossover frequency where the gain equals 0 dB is 20 kilohertz, and the phase margin at this point is 72 degrees. In summary, the emulated current mode control offers all the advantages of conventional current mode control with the following advantages and disadvantages. The main advantage is that it reliably achieves very small on times necessary for large step-down applications. All of the intrinsic advantages of current mode control are retained without the noise susceptibility problems often encountered from the diode reverse recovery, ringing on the switch node, and the current measurement propagation delays. During short circuit overload conditions, there is no chance of current runaway, since the inductive current is sampled before the buck switch is turned on. If the inductive current is excessive, cycles will be skipped until the current decays below the overcurrent threshold. The advantage is that the maximum duty cycle now has to be limited to less than 100%, since there's a requirement for forced off time each cycle for the sample and hold. In the case of our new devices, there's a 500 nanoseconds of forced off time each cycle. In summary, emulated current mode control offers all of the advantages of conventional current mode with the following advantages and disadvantages. It reliably achieves small on times necessary for large step-down applications. All of the intrinsic advantages of current mode control are retained without the noise susceptibility problems often encountered from diode reverse recovery, ringing on the switch node, and current measurement propagation delays. During short circuit overload conditions, there is no chance for a current runaway condition since the inductive current is sampled before the buck switch is turned on. If the inductive current is excessive, cycles will be skipped until the current decays below the overcurrent threshold. The only disadvantage is that the maximum duty cycle is limited to less than 100%, since off time is required for the sample and hold measurement of the diode current. There is a 500 nanosecond of forced off time each cycle. An extensive suite of online tools is available on the National Semiconductor website to aid the designer when using the new family of emulated current mode control simple switchers. Simply input your design parameters, such as input voltage range and output voltage and current. A semi-custom design will be created for you. You can then simulate your design both electrically and thermally. Finally, if you wish, a custom prototype kit can be rushed to you overnight. Before closing, I would like to present a circuit that can be used to create a minus output from a positive input. If you look at this circuit, it is very similar to the buck regulator, except the inductor and diode have been swapped. Since the main switch Q1 is in the same location for each configuration, a buck regulator IC can be used for either topology. When Q1 is turned on, the input voltage Vin is applied across the power inductor L1. Current in the inductor ramps up during this on time. When Q1 is turned off, the inductor current continues to flow through C1, the load resistance, and D1, establishing a negative output voltage. During the next on time of Q1, the load is supported by the output capacitor. Shown on this slide is a complete schematic for a minus 10 volt buck boost regulator. The 75 volt capability of the LM5576 is necessary since the IC sees the absolute voltage difference between the input and output voltages for this application. This concludes my presentation. Emulated current mode control retains all of the intrinsic performance and ease of use benefits found in conventional current mode control with reduced noise susceptibility and high operating frequency. The next generation of simple switcher buck regulators utilizes this emulated current mode control, allowing the user the ability to optimize the size and performance of their solution. These next generation simple switchers are available with output current capabilities of 0.5 amps, 1.5 amps, 2.5 amps, and 3 amps. The maximum input voltage capability is offered as either 42 volts or 75 volts. An online design and simulation tool, WEBENCH, is available for each device. More information such as design tools, application notes, data sheets, evaluation boards, and samples can be found at the national website.